Recall the path we took when analyzing the P0 problem. We started by proving that a sufficiently sparse solution is unique, and then turned to prove that pursuit algorithms are guaranteed to find it. Following this line of work, now that stability has been established, we move to discuss the performance of pursuit methods. However, rather than diving directly into the specific algorithms, we start by addressing several more general issues. Interestingly, the very same stability we have just proven could be generalized in a very easy way. Assume that x0 is S0 sparse, and we create B from it as before. Now assume that a chosen pursuit algorithm has been used, leading to a candidate solution x hat with S1 non-zeros. We assume, of course, that x hat obeys the epsilon constraint. Then, using the very same proof, we get that if S1 is sparse enough, then x hat cannot be too far from x0, thus getting stability for any pursuit algorithm. The question that remains, of course, is why such algorithm succeeds in the first place, a question we will address shortly. Another general question that should bother us is this: what is the best that we could expect from a pursuit algorithm? This question is critical, so as to set our expectations straight. So let's answer this question. An S-sparse vector x is generating the vector b, and let's assume that b is perturbed by a random Gaussian noise of variance sigma squared. Therefore, the L2 squared of the noise vector v is n times sigma squared. We will apply pursuit algorithms for recovering x, and we are interested to know what is the best scenario to expect. The answer is this: a perfect recovery of the true support of x, that is, identifying the exact location of the non-zeros. An immediate follow-up question is this: suppose we succeed in recovering the perfect support. How close can we get the non-zeros to align with the original ones? How much noise will remain in the estimated x hat? Turns out that these questions are relatively easy to answer. This scenario is known in our field as the oracle performance. We start our analysis. The support is known, and thus we solve a least squares problem to find the non-zeros. AS is a submatrix of A containing only the proper atoms, and Z stands for the non-zeros to be evaluated. We have a closed form expression for the optimal Z vector. And now we compute the distance between the original signal, AS times XS, and the estimated one, AS times Z opt. We plug the expression of Z opt and proceed by replacing B by AS times XS plus V. While the obtained expression may look daunting, the appearance of XS vanishes, and we remain with this simpler term. We proceed our analysis by multiplying the term inside the norm by its transpose. Observe that some elements cancel out, leading to a simpler expression. Our next step is to exploit the property of the trace operation, enabling us to shift AS transpose times V from the right to the left. Since the entire expression obtained is a matrix, we need to compute its trace. The expectation is applied on the only random part in this expression, being V times V transpose, and this equals an identity matrix times sigma squared. Using this, all the rest cancels out, and thus we should compute the trace of an identity matrix of size S by S. The final result is sigma squared times S. This is a wonderful outcome, as it implies that the noise has been attenuated by a factor S divided by N. Thus, if S is much smaller than N, this implies a high-quality denoising effect. Just to complete this story, we repeat everything we did, and this time compute the error in the representation domain. The error now is computed by the difference of Z opt from XS. Following the same steps, we get to a slightly different expression that again has no appearance of the original XS part. Proceeding with this analysis, we apply the same algebraic tricks, exploit the known autocorrelation matrix of the noise, and end up with a slightly different result. What is the trace of the inverse of AS transpose times AS? Well, we actually know something about it. Recall that the eigenvalues of AS transpose AS are in the range 1 minus delta S to 1 plus delta S, where delta S is, at most, S minus 1 times the coherence. The inverse of this matrix will have the reciprocal of these eigenvalues. Thus, the trace of this matrix is upper bounded by the maximal eigenvalue multiplied s times. So we see that even in the representation domain, the oracle error is of the order of s times sigma squared. Let's summarize. If x is an s-sparse vector and we generate b from it, then solving p0 epsilon or approximating it makes sense. It will result with an estimated x hat that is not far from the original x. And furthermore, if the support of x is recovered, we will get a strong denoising effect, which means that much of the noise will be attenuated. We turn now to analyze three specific pursuit algorithms: the basis pursuit, the thresholding, and the OMP. We should note, however, that our presentation will focus on the simplest possible analysis, one that takes a worst-case point of view. We do so in order to keep the discussion simple.